Uh, I'm going to talk on a very interesting technique, elevating plant reliability, exploring the latest advances and applications in in-situ metallography. Uh, we all know that today's time, there are a lot of pressures on industry to ensure that the reliability of the component increases. Uh, and also, there is a pressure on industry for the plant life extension. So it's important that we understand different damages and different damage mechanisms, and we can identify the early onset of those damages. And we have to identify the life of an equipment or a warning for early replacement or maybe continued with caution. These kind of suggestions are very welcome by the plant operation and maintenance department. So the roles and responsibility of inspection department as well as the metallurgical expert is to ensure that the in-situ metallography is done in a professional and with knowledge aspect, so that the right judgment on the plant assessment can be taken. Now, we all need to understand the damage with early warning. This is something which we need to understand, and we have uh, different equipments in the plant where normally static equipment and rotating equipment are divided, and also there are structural components of the plant which needs further assessment. So there are different aspects of damages where thickness loss, which can be general or localized, or there can be a very insidious thickness loss through very heavy pitting, or there can be localized damage because of the CUI. So there are different damages. Cracking can occur because of thermal fatigue, mechanical fatigue, stress corrosion cracking, fretting fatigue, corrosion fatigue. There are many cracking mechanisms, but these are the major ones. Then you have a creep damage, which is also associated with dimensional change. And there are metallurgical degradation with the aging effect, which is gaining a lot of attention in today's high temperature components like heaters, boilers, then temperature equipment which are operating more than 300 degrees centigrade temperature. And there are other damages like disbonding, oil decay, improper heat treatment, weld flaws. If you see in rotary equipment, there are a lot of other damages like mechanical damages, dents, scratches, wear on bearing, cracking also the same as static one. Creep, then you are a lot of having corrosion damage, and then again a creep damage is possible in turbine and high temperature components, and metallurgical degradation is equally possible. Same thing in structural equipments, we have a thickness loss because of atmospheric corrosion, mechanical fatigue, corrosion fatigue, static fatigue, then different corrosion aspects on lifting equipment and corrosion for over the sea and on ground equipment, and seashore also there are a lot of corrosion problems. So there are different damages which we understand, and we are trying to find them the catch at the early stages. So how do we detect them for early damages is through different non-destructive testing, of course, where you can see have the visual examination, thickness mapping, radiography, latest equipment. So I'm not going to go into the all entity technique, but in-situ metallography is something which is done at the site, and the microstructures are transferred on a plastic tape, which are observed above 100x magnification, and many times it can go up to as high as 10,000x magnification with the help of electron microscope. So most importantly, in-situ metallography is done in today's case for aging, to find out the aging of the equipment, creep damage, if the basic heat treatment is not proper, or there is a mixture of material, or there are early warnings of certain fatigue damages where very costly equipments can be saved. So when I gave a lot of stress on these damages, I am trying to give you an insight that the without metallurgical knowledge, in-situ metallography as NDT technique has not gained a success. If you see a lot of people, those who are trying to do in situ metallography, when the report comes to me for review, most of the time they only try and put the remarks which is written in these standards or handbook. But one can get much more information and detail for the plant assessments if they are involved into the understanding of damage mechanism, and hence a replication technique has to be done by the person or the company who has the experience in damage mechanism. Now, there are different damage determination technique, which I'm trying to highlight here, where, the material's hardness will change if the material is in the aged condition. Tensile properties will change. So there are small specimen test punch which are taking out small toughness, and there are creep strain measurement devices are kept on the equipment. But the microstructural damage is, one can identify through metallurgical degradation from interparticle spacing, because metals are made up of different metals in form of alloys, and those are forming certain carbides, certain intermetallic phases. Those are used for strengthening mechanism also, and then you can find out from interparticle spacing. Then there are cavitation parameters which is used in creep damage, where very accurate RLA, remaining life assessment, is possible. This is greatly used in the field of boilers, whereas Indian boiler regulations have made in situ metallography compulsory to find out different damages, and they have categorized in different levels of damages, and one can find out the remaining life. Then there are density methods, number of density of cavities also you can find out, volume fraction and area fraction. So basically, microstructural degradation are used for different techniques to identify the life. And there are others methods like, ultrasonic resistivity and density. They are different methods. So, we'll not just an overview. We are trying to create an understanding that microstructural aspect has the uh, capacity to identify different parameters as well. So this is where the technique needs to be applied properly. Now, when you use the definition of metallography, the metallography is defined as an art and science of preparing the microstructures of metals and alloys and its interpretation. So there are two aspects which are very important when you conduct in situ metallography. The one is preparing of microstructure itself. So it is always considered as an art. So there are different metals and alloys, and people, those who are performing metallography, needs to have the very soft hand to produce scratch-free structure. They must be aware that where to apply pressure and which consumables are to be used. So there is an art plus science of preparing the structure, and very, very important, where most of the people are missing, is the correct interpretation. So correct interpretation comes through the subject knowledge. So, and once you have this, then one can identify the early. Many times you need not to go for a very sophisticated equipment to identify the damages, when you can genuinely get the early warnings through the application of in situ metallography. Now, if you see this one microstructure which has been kept, because whatever microstructure you prepare and see in the laboratory or on the replication structure, it is always in 2 dimension. But actually, metal component is it in 3 dimension. So, this is the image of the gray cast iron, where you can see the graphite flakes. And then if you see the 3-dimensional view of the graphite flake, it is like one which is depicted in the pink color, where you can see, and whenever you cut, such edges will come. So actually in 3 dimensions, so this knowledge is very important when someone is interpreting the microstructure. That what you are showing is 2 dimension, but actually the damage occurs in 3 dimensions. So this fundamental is very important. Now, basically you have to understand what is in situ metallography. In order to understand, we need to understand what is metallography, what is routine metallography. So, routine metallography is one which was invented in the 18th century by one Mr. Sorbet, Professor Sorbet, who was a geologist, and he started developing the structures of the metals and materials especially. And then over the time, the technique further refined, and today one can identify the microstructures and understand all the properties. So a small sample of the metal is cut and it is polished against the different abrasive materials, and then you make it scratch free up to a mirror finish, and then you apply a little bit of chemicals so that the micro level corrosion occurs, and at the grain boundaries you see uh, different ditches, and those ditches are actually seen as grain boundaries. So depending upon the etching, you can see thick grain boundary, thick grain boundaries. The different phases are etched differently, and then colors are being seen. So we will also see how light microscopy affects the microstructure. And then in what is in situ metallography? The in situ metallography is instead of cutting the sample, you take the entire kit to the equipment, like dentist who does the preparation in your teeth. Same way, the components with the rotating shaft and the other wheels are kept where the different abrasive material or the papers or the cloths are provided. And then you polish the very small area of the metal surface. And then you again apply a small amount of chemical, and then the structure is developed, and then again transfer on a plastic tape, which is known as replication. So, if you compare both, one is destructive and one is non-destructive. Hence, in situ metallography has taken a lot of attention in these days. And I'm very proud to say that from TCR Advance, we have more than 30 teams who works day and night in the entire country to provide different metallography. And those companies, those who are involved with TCR, has gained a lot of benefit, as now they are trying to monitor the damages and they are extracting the extra life from the equipment without having a danger of failure. So for routine metallography, there are no limitation, but for in situ metallography, we have a limitation that you can only access to the surface. Same way, you cannot access the area where your hands cannot go. It's like, whatever components you can build, you can do microstructure. That is the thumb rule you can think. In cross-section metallography, you can study the bulk structure also, because you can take the sample anywhere from the metal, whereas it is only in the surface. And it's a major useful in find out the remaining life assessment of the equipment, plus the early warnings of different onset of damage, where you can improve the process by guiding the plant. And hence there are different applications of both the metallography. I'm not going to go into the details of this, but the major useful aspects of in situ metallography is health assessment of critical components of process plants operating at high temperature and high pressure. This is very routinely done. Then when there is a damage in terms of fire or any bulging which has occurred or any process upset which has occurred, TCR Advance has given these services to the Indian industry in all fire damage assessment, all major fire damage assessment in the country. Then, you can also use it for quality check for various metallurgical process and heat treatments. Very costly components are being, brought from abroad or within the country, where the right amount of the material, and suppose if fails in the operation, it can give a huge problem. Then, quality control check is very important. We have done, this kind of quality control check on many components. In one of the plant, there were about 600 plus flanges which were having a doubt whether they were heat treated properly or not, so or whether they are as forged. So TCR was contacted, and then we identified out of 600 about 200 wrong use of different flanges, which was giving a lot of failures and a lot of downtime was occurring. Same way during fabrication, if the welding cracks are occurring during components, people use the metallography to identify whether the heat treatment is right or not. Or also in critical components like stainless steels, when they are manufactured or heat treated, because the carbide precipitation in the grain boundary is a serious problem. So, before you put the equipment into the operation, you can judge the heat treatment is right or not. So, it also helps in to generate the data on imported components, because many times the cost of the components or the spares are very costly. So, before you put them into the operation, you can check the microstructure without destruction, and gets the important information for indigenization. It is very useful in failure investigation. We have been using it day in and day out for a very long components, where only small fracture samples are being taken into the laboratory. But for the away locations where you need not to take them into the laboratory, we check the microstructure as side. And very, very useful technique for provide the repair building decisions, especially when components are nitrided, when there is a high temperature damages which are occurring. And we, based on in-situ metallography, we have provided the solutions for on-site solution annealing of the components also. So they help in providing very useful solution, and a very costly downtimes of the shutdowns can be reduced by in-situ metallography. Now, there are two important aspects. One is the process of in-situ metallography, and the other one is the equipments for in-situ metallography. So if you see, very, very important aspect is which area needs to be inspected in the plant, where knowledge plays very important role. I always say that the location selection is more important than the microstructure testing itself, because you have to identify the critical areas. And I always appeal to the plant, because plant in India, our companies have been knowledgeable to do metallography, but I still there is a lot of gap doing in which area the metallography is to be done. So I appeal all the industrial people to do better study or consult experts for the location selection. And once the location are selected, then the metallography will give you much better results, especially damages will be identified much earlier than the anticipated. In comparison to the locations where damages are not there and you may get the wrong judgment. So, it has to be done by proper visual examination. So what we can do walk the plant, and we can identify. Once you identify the location selection by doing a study of operation and the past history of the failures, small area is selected, then it is the oxide layer removal from the surface is very important. So you have to do grinding, then you go for polishing with different papers, and then you go the polishing with alumina, or also you can do electrolytic polishing. And then you can etch the structure by applying the little bit of chemicals with the swab, cotton swab, and then you do a microstructure examination at site, and then take a replication. So there are portable grinders, portable polisher, portable electrolytic etcher and polisher, portable microscopic kit, replica kit, and consumables. So all those equipments are needed, which are provided in the images. And then there are different steps. One can do manual polishing, and another can do electrolytic polishing. TCR is using both. If the components are in higher number, electrolytic polishing are used, because in plant electrolytic polishings are normally avoided, because the chemicals which are used in confined space can create problem. But oxalic acid etch test electrolytic polishing is etching is very safe. So manual polishing and other techniques have been identified to do this. This is the work in progress, where the gentleman is there doing metallography in the boiler tubes. He's doing in the reformer tubes. And now in today's time, there are portable microscope with camera available, where you can directly transfer the image from without taking replica. Also it is possible, but we advise to take replica, because here the limitation is only you can check up to 200 to 400x, but in laboratory you can go for 1000 to 5000x magnification, sometimes 10,000 if needed. So replication is there, but many times judgment can be taken by and nowadays people ask us to shift the laboratory microscope at site itself. So replica testing is done at site, and immediately on the same day the results are given. So that is also we have done it a lot many places. Then further, if you see, when you take the microstructure of replica, it's an inverted image or a negative image, where when you etch the material, there is a response of the material corrosion occurs at a micro level, depending upon the grain structure, or the phase is present, or a carbide are there. So when the structure is etched, when you place the plastic film against the surface, the negative image comes. So in both the cases, when the light strikes, the same image appears. So the microstructure observations remain same, but the replica is a negative image. It's important to know and understand. Having said this, there are laboratory optical microscopes which you can put the replicas, and then you can check the microstructure on a computerized setup. Then, having taken the microstructures, one should take the replica on a storage rack, and then the preservation of replica samples are very, very important, because when you are monitoring it every 2 years or 1 year, the previous record of microstructure is very, very important, especially when you are taking a very critical decisions. So this kind of racks are very useful. Then many times, if you want to find out certain damages which are creep related damages, or certain very fine analysis of the fine dispersion of the different phases, then the replica microstructures are sputtered with the gold and then put under electron microscope. I'm extremely proud to say that TCR Advanced has now 3 electron microscope in house, which is working parallelly, and we are helping not only in India, but a lot of work are coming from abroad also. So those are the image. This is the latest edition of SEM, which has been very compacted, and we can analyze around more than 27 samples at a time. So having said this process, that is art and science of metallography, now it is important to understand the metallurgy behind the microstructure, and then one can provide the proper analysis of the replicated structure. So it's important for people to know that what are the stability of phases in carbon and low alloy steel, which are the major workforce of the industry. And then, the stability of the structure, one should understand that the most unstable structure is martensite, then benite, then para-equilibrium ferrite and para-equilibrium cementite, then ferrite and cementite, ferrite, graphite, and cementite is the most stable. So most of the time, if you operate the material more than design temperature, the resultant structures will be ferrite, graphite, and cementite. So this structure tells you that a lot of degradation which has occurred, and the mechanical properties are at problem, and then cautions are always sought here. Then damages detected on microstructures are graphitization. We will see in the subsequent slide or what are all these damages. Then degradation of perlite, decarburization, creep, thermal fatigue, mechanical fatigue, IGC and grain dropping, oxidation, grain growth, hydrogen attack, sigma phase detection, the other stress corrosion cracking, pitting, and selective leaching. So these are the different damages one can identify through microstructure and metallography, especially non-destructively, by selecting the right locations and understanding of these damages, thorough understanding of these damages. So what is graphitization? Now, graphitization is the damage which occurs to carbon steel, especially or carbon half moly material, when the prolonged exposures in the range of 400, sometimes 400, 425, where the perlite, carbon from the perlite comes out and forms the carbon plus iron. Because as I told you, the graphite is the most stable form. So system wants to go to its stable phase, and then Fe3C, that is component, that is the cementite from the perlite, will convert into carbon and iron. And once the carbon graphite nodule forms, the carbon steel will behave like a cast iron, because these nodules are formed in a cast iron. So the designers have not considered this aspect, and very catastrophic brittle fracture will occur. We have saved many mainstream line tubes, boilers, in refineries and petrochemicals, and also in fertilizer industries. Once the graphitization is formed, we ask them to monitor, and we ask them to replace the component. So the identification of this damage is very, very important. Then we have decarburization. So when the graphitization is formed in certain furnace environment, if the oxygen potential or a carbon potential is not maintained, the carbon is depleted from the surface. Like in carburization, the carbon goes inside the material. In decarburization, carbon comes out of the material. So decarburization can occur either at the most of the time at the from the manufacturing stage, because heat treatments are done for these components, but they are also possible to be done in the operating environment. And operating environments, once you find out such damages, we tell people to control the carbon and oxygen potential in the environment of the furnace, and then the damages are further avoided. Then you have the degradation of perlite. Now this is a very common damage mechanism where the carbon steel and low alloy steels are quite often used in most of the components. And then when they are operating more than 400 degrees centigrade temperature, the perlite is the alternate lamella of cementite and ferrite. When it starts converting into spheroids, they lose strength and also lowers the hardness. So when they lose the strength, increases. Because when you find out at an early stage, you can improve the operation and get the maximum life of the component. Then you can find out corrosion and pitting damage, from the replication. And you also can find out the type of if you take the extraction replica, you can take out the actually corrosion product on the replication and do EDS. It will give you a lot of insights like failure investigation by a replication. Then one can find out the heat treatment quality in austenitic stainless steel, where a solution annealing of austenitic stainless steel is very, very important, where you want to produce the cleaner grains of the austenite without carbide precipitation. But if the temperature during subsequent cooling is slightly slow in the range of 400 to 800 degrees centigrade temperature, the carbide forms at the grain boundaries and the chromium depletes, and the corrosion resistance goes drastically down. In situ metallography, we have helped industry in a big way in this area, and a lot of failures have been prevented and a lot of components have been reheat treated. Then the major aspect of in-situ metallography is industry is done to find out the creep damage. So creep, we all know that it is a time-related, temperature-dependent deformation under constant stress is known as creep. So there are different stages in the creep. There is a first stage, second stage, third stage, and fracture. So which stage the component is, where is in a primary, secondary, or tertiary, one can really identify through microstructure. And if you can see the microstructure here, you can see isolated cavities, oriented cavities, microcracks, and macrocracks. Now, identifying of this cavity against the carbide is the major art. And most of the people get confused in order to find out the cavities. And then the experience laboratory with experienced metallurgists are very, very important in providing the qualification of these damages. I am sure in coming time, we will have a different levels of people, those who are doing metallography. And I have a wish to start this from our country, that, we can provide level 1, level 2, level 3 in the metallography, so that, people get the right amount of confidence when they call different parties and people. So as I explained here, the curve indicates stage 1, stage 2, stage 3, and stage 4. So if you can identify, all these stages and control the parameters, the creep curve can shift towards your right, and the life to fracture can increase significantly. So instead of, just satisfying these standards and specification, one should integrate this with the operational aspect to get the plant life extension. This is what my dream is for this country, and we can double the life of the plant if we are able to maintain our plant within the operating regime. So once you do this, there are different creep damages observations. One can identify from the electron microscopy, where you can identify different creep cavities. You can see at the grain boundaries, and then further there are certain images for the creep voids, which are also provided on an electron microscope. Then, there are different creep cavities you can see in the weld of a boiler material. So they are directionally oriented, and hence, but I have generally not seen such clear images in other, whenever a lot of report comes to me for review. So, people are misguided rather than guided in these techniques. So the user needs to be quite aware about this technique. Having said this, people are also use this technique for reformer tubes, where the microstructure degradation and coarsening of carbide is one aspect. plus there are micro cracks and the creep cavities which are observed under the reformer tube, where you have a austenitic structure, and then you have primary and secondary carbides. So distribution of the secondary carbides and lumps decides the remaining life of the component. So TCR has the capability of automated reformer tube inspection system, but we always do metallography, in situ metallography in reformer tubes for say about 10 to 20% of the tube, depending upon the condition of the tube. And then, very accurate decisions have been taken for remaining life assessment. Then the other important damage is thermal fatigue. If you see components, if you find out the early warning, this is a stainless steel component of a paper mill digester cone, where we could identify the micro cracks on the surface. And these are the typical onset of thermal fatigue cracks, where cracks are blunted and they are cutting the grains. So we could identify them, and we asked them to grind the surface to 200 to 250 microns, and they were vanished, and the life of the digester plates were restored to original. Similarly, a lot of autoclaves we have said to different chemical and process industries by identifying such damages, and then they are saved for further damages. Same way, thermal fatigue can be identified in the turbine components, especially on the Curtis wheel and the rotor, where you can identify the early warnings. So, once these cracks are deeper, the entire rotor of crores of rupees becomes the obsolete. But if you take a micro cut, if in the early stage, then the life of the rotor can be further increased to original. And these technologies used by GE and other manufacturers like Siemens and Alstom for improving the life of the rotors. So in-situ metallography plays very high role to identify such early damages. And then you have a high temperature oxidation of the component, where sometimes accidentally temperature goes high. If any furnaces, the internal lining of the refractory goes out, then the steel surface is exposed to more than 900,000 degrees centigrade plus, or sometimes 1100 degrees centigrade for a shorter time, where grain boundary oxidation occurs, and it becomes very, very dangerous for a material to survive. So this requires a high amount of experience of a different etching technique to identify this damage. But this is very useful for industrial application. The other application is hydrogen attack, where you can identify the cracks which are associated with decarburization, where methane formation is responsible for the diffused hydrogen at high temperature in the material. And from the perlite, the carbide, that is a Fe3C component, react with the hydrogen to form methane gas as per the equation provided. 4H plus Fe3C produce methane plus iron, and this methane produces tremendous amount of pressure in the material, and fissures occurs. So this is very much possible to identify hydrogen attack damages. Then you can identify the stress corrosion cracking. We have identified n number of samples and prevented a lot of failures and damages to many chemical and petrochemical industries, even in fertilizer industries, where early onset of such damages were identified and the disasters have been prevented. Then sigma phase detection. Now this is something which is, in my opinion, going to be a very big requirement in the few coming time. That is for power plants, where a lot of power plants are now coming on the components with the stainless steel, especially the supercritical components, or also in subcritical, the final superheater tubes are made of 347 material. So the all 304, 316 and 347, 321, they are susceptible to sigma phase formation in these material. And once the sigma phase formation occurs beyond 10%, it started reducing the mechanical properties and corrosion properties drastically down. So the people start replacing these components. So if you are not operating your components within the design limit, these sigma phase formation occurs. So these become the useful tool to put a check on the operation, to put a check upon early warning. And we have been doing a lot of sigma phase identification in these power industries, and also in the refinery section, where 347 material is used at a high temperature. As I told you in reformer tubes also, there are a lot of cracking, early cracking of damages where thermal shock is a major problem, especially when the process upset occurs. And then those processes are providing the zigzag cracks at the interdendritic region. And you know how many tubes are affected. Suppose in starter 5 or 7 tubes are failed, then you need to identify other tubes in the surrounding region. So along with other NDT technique, metallography provides very important evidences of such damages. So overall, if you see, there are a lot of benefits of in situ metallography. It can provide you preventive maintenance and inventory control for plant life extension. This has been used extensively where the inspection people are knowledgeable, and TCR is committed to provide knowledge on in-situ metallography. From Evolve, we conduct the 1 or 2 days complete programs on in-situ metallography, and I encourage people from different industries to join this program so that when you become knowledgeable, you can utilize this technique in the right perspective rather than only using this technique as advanced technique and providing the certification on IBR. Then you can also use this and monitor the damages to the plant components. Many times, there are certain damage which occurs to the equipment or a component that does not necessarily requiring the replacement, but it is very much requiring monitoring. So every 2 year, if you monitor the microstructure and find out that there is no degradation occurs further, then those components can be extended for another 2 years. So monitoring the component is very important. It also provides you safety and reliability of operation where certain damages like hydrogen attack or SCC occurs or thermal fatigue occurs. We ask them to replace the components or remove the surface layer to ensure the use of the correct metallurgical status of the component. Uh, and I can share n number of examples where very costly Hesloy materials, costly nickel-based materials, stainless steel materials, high temperature components, they were received and failure occurred. So we could identify even in inventory what will be the suitable components to put inside rather than the wrong heat treatment components were identified. So this is something people can utilize to reduce the downtime and especially prevent the failures by adopting or putting it the right component in the plant. Then it is also useful for indigenization or localization of imported components. TCR has provided consultancy for indigenization for huge number of components and very successful. So it provides the secrets behind the imported components and also used as a quality control on produced components. And once the quality control is streamlined, you can get the better life than the imported component also. And it is very useful in repairing decisions of the used components, especially on the outlet headers of reformers. Then reformer tube itself, I am tempted to tell you that in one of the company during startup there were about 100 I think about 60 to 70 tubes failed out of 300 tubes. And the plant had a lot of pressure to restart the plant. They had only 40 tubes. So we could reclaim the another 20 tubes from the damaged tubes, the good area of those tubes. Then the plant was put back into the operation, and that was something not possible without in situ metallography. And also nitrated components, how much to grind, then whether the headers require solution annealing heat treatment or not. This is all possible by in situ metallography. And as I told you in earlier, the success of in-situ metallography depends on the location selection. I'm putting this, after these damages and providing the knowledge in the end, this slide where you should give two consideration. One is structural consideration, that is weld joints, T joints, change in cross section. Because in welding, we know that there is a weld metal, parent metal, and heat affected zone. So all these material has a different microstructures. So certain damages occurs in HZ, some damage occurs in weld, and some damage occurs in parent metal. So you have to identify which damage will occur at which location. Then T joints are normally more stressed. So certain damages which are related to stress will affect more there. Then change in cross section of the pipe and tube. and sometimes, change in the material of construction also. So bend stress generated due to self weight is very important, where, say 20 or 15-meter long pipeline coming from the top, when it is welded at the top, it is most stress region, because the self weight of the pipe is also in consideration. So those areas will give you early damages. Or process consideration, if you see pressure and temperature, direct gradient zone, place of MOC change, as I told earlier, outlet headers, location with prior history of the failure. So here I want to tell you one guideline, that whenever you want to do in situ metallography, take a reference location of the same component away from the high temperature or a stress region, so that, you can compare the microstructure, and, it is possible to convince management that degradation has occurred in the same component. So TCR has taken a lead in providing the, awareness in this field, and we have provided this microstructure chart, where, early damages and degradations have been provided in a single picture itself. You can contact us for a free copy of a high resolution copy if you want. You can contact our team. We will be more than happy to provide this and generate the knowledge in this area. So, in the end, I would like to thank everyone for joining on this knowledge sharing session, which is the lead taken by you all, by TCR. And I thankful the entire team for organizing such issues, such knowledge sharing webinars that helps. I'm going to talk on a very interesting technique, elevating plant reliability, exploring the latest advances and applications in in situ metallography. We all know that